visit and meet in Trento for discussions of hadron physics, so I thought we'd start with that. Some background. This collection of lectures provides some of the information that I will use to supply material for these lectures. I see some people from Brazil smiling because I spoke in Brazil a few years ago, down in Rio de Janeiro state. It was very nice. This set of lectures was some mathematicians in Strasbourg, a very different audience from what we normally have. And a couple of lectures I gave, a series of lectures in Rostock in 2 semesters, and they are quite pedagogical. And this original review article with Tony Williams appeared many years ago, but still is useful for providing material to support these lectures. So the material will be focused on the standard model of particle physics. We won't go beyond the standard model, or at least I won't. And the background is the early 20th century. We knew then that we had a proton, a neutron, and an electron, and that is all. And then we developed cosmic ray science. I saw a photograph of Cecil Powell in the corridor. He's one of the people who invented the technology needed to use cosmic rays to study particle physics. We found the muon in 37, the pion in 47, the kaon at the same time. Later we found the first excited state of the proton. And after a few more years, it was realized that not all of these particles could be fundamental. A new paradigm was necessary. And we looked to chemistry, where we brought order through the periodic table, and Gell-Mann and Zweig independently came up with a constituent quark theory in 1964. And Gell-Mann was recognized for that a few years later, for his contributions and discoveries concerning the classification of elementary particles and their interaction. They realized that all of the states that they had discovered could be unified by just thinking of them being composites of 3 fundamental objects, 3 types of quark. So from this period, 64, over more than 50 years, we developed the standard model of particle physics, which still manages, it seems, to pass most of the tests that we present for it. It is not complete. It's the most complete theory that we have of hadrons and all of the other particles that we know of. The only problem we have, seemingly, or the biggest problem we have, is unifying this with gravity, which we cannot yet do. The pieces of the standard model are generally well known. There is electromagnetism. This was developed in a period of 5 years, and the major discoveries were by Feynman, Schwinger, and Tominaga. And they received the Nobel Prize in '65 for their fundamental work in quantum electrodynamics, with massive consequences for the physics of elementary particles. This was the first relativistic quantum field theory, the first time that we'd put together a quantum field theory and understood how we might make sense of all the integrals that diverge when you start to calculate loops in quantum field theory. Later, it was the weak interaction was unified with electromagnetism. Radioactive decays, parity violating decays, electron-neutrino scattering. This was a period of 10 years. Glashow, Salam, and Weinberg put this together, primarily. And they received the Nobel Prize in '79 for their contributions to the theory of the unified weak electromagnetic interaction between elementary particles, including, amongst other things, the prediction of the weak neutral current, which was later verified. And finally, the strong interaction. This is the theory that's responsible for the existence and composition of the vast bulk of visible matter in the universe. The proton, the neutron, must be described by the strong interaction, the forces that bind them and form them, and it's responsible for more than 98% of the visible matter in the universe. Everything that we know of, that can see and touch, almost all of that material is described by the strong interaction theory. The Nobel Prize for QCD, you might say, was given to Politzer and Gross and Wilczek, who independently, almost, appreciated that the running coupling in QCD behaves completely differently to that in electrodynamics. It runs the wrong way. They discovered asymptotic freedom in the theory of the strong interaction, and we'll talk a bit more about that as we go along. We know only about 4% of the matter in the universe. 76% is probably dark energy, another 25% is probably dark matter. We can see about 4% of the matter that makes up the universe, and that is primarily determined by the properties of QCD. So it's very important to understand what QCD actually does. The formulation of the Standard Model is, in some sense, quite simple. We have a Lagrangian. It's a local gauge field theory, and there are three gauge groups, a cross product. And this gauge symmetry underlies the basics of quantum field theories. And there are 19 parameters in the Standard Model. And they must be determined through comparison with experiment, because physics is, after all, an empirical science. The weak sector, electroweak sector, has 17 parameters. And most of those are connected with the Higgs boson, the things that give us the current quark masses and the masses of the electron, the masses of the W boson, the Z boson. All of these parameters are locked up in the weak, electroweak part of the Standard Model. That sector is essentially perturbative, so the parameters are quite well and quite easily determined. You can use perturbation theory to pin them down. The strong interaction component is completely different. This is a strong interaction part. Only two of the parameters are present in that sector of the theory, and one of them might actually be zero. We can't be sure. One of them we have to measure. So the theta parameter in QCD is constrained by observation to be less than 10 to the minus 10, and that would be the strong CP part of the interaction. Lambda QCD, the mass scale for the Standard Model, is what sets the scale for you and I. It has a value of about 0.2 GeV. We can't predict that. No approach to the Standard Model can predict that. It's something external. Maybe a theory beyond the Standard Model will give us a value for this in the future, but at the moment we can only know it by measuring it. Lambda QCD. And the impact of these two parameters is not fully known. That's why we're here. That's why we study QCD at the deepest level. The Standard Model has a very well-known particle content today. We have the 6 flavors of quarks. We have the leptons and the gauge bosons. We invented the Large Hadron Collider, built it, constructed it. The cost was $7 billion at construction time. It accelerates particles to almost the speed of light in 2 parallel tunnels. Each is 27 kilometers long and lies 175 meters underground. And those beams collide at interaction points. The experiments take place at those interaction points. During a 10-hour experiment, each beam travels about 10 billion kilometers. That's about 100 times the distance between the Earth and the Sun. That's what's going on for a 10-hour experiment at the LHC. And the energy of the collisions reaches now 13 TeV. The LHC is just closed down. It's being upgraded for a new series of experiments in a few years' time. And the LHC did what it was supposed to do. It discovered the Higgs boson. This is not actually an observation, it's a simulation that shows what a Higgs boson event looks like. The Higgs boson decaying into 4 muons, a signature observable for the Higgs boson. 4th of July 2012, I don't think Independence Day was really instrumental in the discovery, but the experiment was then successful. Both experiments, Atlas and CMS, found an object at 126 GeV. This is consistent with the Standard Model's prediction, the same types of characteristics, and so that is called victory and said we found the Higgs boson. There are other types of Higgs bosons predicted by other theories. This one seems to be what the Standard Model predicts, but we can't say much more than that just now. So that was it. In 2000, Higgs and Englert were awarded the Nobel Prize for the notion of the Higgs boson. And with that discovery, the Standard Model became complete. And as I've seen, and you all know, the formulation of this took 100 years to put together. And so far, it seems to be an almost complete theory of what we can do with nature. So we're left with the question, and many people ask that, Where do we go from here? If the standard model is complete, what are the questions we should be asking ourselves now? So I thought I'd go back in time a bit to find out where to look next for those questions. We're here at the Galileo Galilei Institute, and Galileo was born about this time of the month many years ago. He's been called many things: the father of modern physics, the father of the scientific method. He was a polymath. He studied almost everything: speed of velocity, gravity, free fall, relativity, classical relativity, not special or general relativity, inertia, projectile motion. He worked in applied sciences and technology and described pendulums. He was an observational astronomer, telescope, studied the phases of Venus, discovered the 4 satellites, largest satellites of Jupiter, the observation of Saturn, and the analysis of sunspots. He also championed the idea of the sun being at the center of the solar system. This was not popular when Galileo was alive. In some parts of the USA, it's still not popular. He was tried twice. In 1633, he was found guilty by the Inquisition for heresy because of this idea that the sun was at the center of the solar system. He then spent the rest of his life under house arrest, and while under house arrest, he wrote 2 more books in which he summarized the work that he'd done some 40 years before this on what we now call kinematics and material strengths. This is a particular example of the slow-moving wheels of justice. It wasn't until 1991, with a front page article in the New York Times, that Galileo was reported to have been found innocent of these crimes. And he was forgiven for asserting this notion that the sun was at the center of the solar system. At the same time, we had Clinton and Bush fighting for the presidency of the USA, the first Bush. So this is a notion of dogma. When you have a principle or set of principles laid down by an authority as incontrovertibly true. We sometimes have that in science. We are told that things are true, and we should just take it as gospel. But science isn't actually meant to be like that. And what I'm going to talk about here in these lectures will be things that we can talk about, discussions. As Jani said, you should involve yourselves, ask questions, because science is an intellectual and practical activity where we study the structure and behavior of the physical and natural world through observation and experiment. And the scientific method, pioneered by Galileo, is that of discussion. We criticize one another in a friendly fashion. We discuss the questions that we raise, and we come to a point where we agree. And agreement doesn't mean that it's right. It means that it's good enough for the present, because science evolves. Science is not static. The pictures change. We understand more as time goes by. This brings us to another point where it's maybe becoming dogma now, we might want to think about. This is a summary of what we think of as string theory. I just had an awesome idea. Suppose all matter and energy is made of vibrating strings, very tiny ones. Okay, what would that mean? I don't know. This is an article from The Guardian, the online paper now primarily, but used to be called the Manchester Guardian. And it talks about when in 2012 they discovered the Higgs boson. Champagne corks flew all around the world. 80 years in discovery, we had completed the standard model. Inevitably, a hangover followed. The leading idea of how to push physics beyond the standard model and explain the remaining mysteries of the universe is looking shaky. Thousands of physicists have spent their career carefully constructing supersymmetry and string theory. And the Large Hadron Collider has not found any evidence to back up this theory. I was at a conference in Chile 1 year ago with many high-energy physicists, and the high-energy physicists opened their presentations with an apology. I'm sorry, we haven't found anything yet. The nuclear physicists were very excited. They come there and they have all sorts of new facilities being built, all sorts of new discoveries in mind. The difference between these two communities was quite marked. This conspicuous lack of proof has led a growing number of physicists, particularly those who are less invested in supersymmetry, to publicly call time on the idea Perhaps, despite all the work, the theory is just plain wrong. Well, some people didn't want to hear that. So they have a different approach. Faced with difficulties in applying fundamental theories to the observed universe, some researchers have called for a change in how theoretical physics is done. This was published in Nature. They argue explicitly that if a theory is pretty enough, you don't need to test it experimentally. This takes us back some 500 years to the fight between empiricism and rationalism. The empiricists were on the island of the UK. The rationalists were on the main continent of Europe. And there was a big debate, actually a fight, a bit like Brexit now, perhaps. Chief amongst these elegance will suffice advocates are string theorists and cosmologists. This is not science according to Galileo. And it's also not science according to one of the most famous PIs ever to have maybe not lived. Sherlock Holmes said that I have no data. It is a capital mistake to theorize before one. Insensibly, one begins to twist facts to suit theories instead of theories to suit facts. So again, physics is an empirical science. Theorists have to face this fact that no matter what you say, it doesn't matter how loud you say it or how pretty the equations you are using, it's not true unless it's validated by a body of experiment. We learnt this, as I said, 400 years ago. It's not physics unless it can be tested empirically, and it's not proven unless it's verified experimentally. This brings us back to the beginning. The God particle, so-called. The LHC has found the Higgs boson, but it has not found the God particle, because the Higgs boson is not the origin of mass. The Higgs boson produces a little bit of mass. The current quark masses for the up and down quark, for example. These are very small. 2 MeV for the up quark, 4 for the down quark. Those mass scales don't explain why the proton's mass is 500 times bigger. They don't explain why the pion is nearly massless. So, despite having completed the standard model at the high energy end, the LHC has as yet taught us very little about the origin, the structure, and the nature of the nuclei whose existence supports all of the cosmos. We have to go beyond this so-called God particle. Strong interaction sector of the standard model, QCD, is the key to understanding the origin, existence, and properties of almost all known matter. This is nuclear and hadron physics. This is really a frontier inside the standard model, where we need to go to understand what the standard model actually means. QCD, as we'll see, is essentially non-perturbative, and it's very hard. We have no experience with studying a fundamental non-perturbative theory. The formulation, as I said, is sort of simple. You can write it down on one page if you write small enough. In there is the most important part. The rest of it is perturbative. But this part of QCD has this gluon field strength squared. That forms the field strength tensor for the gluon, and those gluon self-interactions generated by this term are the most important part of the standard model. They're responsible for the gauge boson self-interactions, and somehow they're responsible for 98% of the visible matter in the universe. That's why I will focus in these lectures on QCD and hadron physics. It should be said, of course, as I've said already, that the standard model is not complete. We know that neutrinos have mass. This evidence has been accumulating for 30 or more years, but we confirmed it 10 years ago with the Submarine Neutrino Observatory and the discovery of neutrino oscillations. We know neutrinos have mass, and that's not part of the standard model. You could probably fix it up in simple ways of extending the standard model. You don't need to have a new paradigm to change that. But the existence of dark energy and dark matter suggests that something very important, something very big beyond the standard model also exists. There are many places to go. Heteroweak symmetry breaking, ground unification, putting gravity in, for example. We don't know how to do that. Many ways of doing it and many speculations. Given 100 theorists in the high energy sector, there are probably 100 different ideas for how to extend the Standard Model. This is what we do know. This is what we don't know. Dark matter, dark energy. There are open questions in many areas. And at the turn of every millennium, groups of well-fed people like to gather and decide what the top questions are for the next 100 years. This happened when the 19th century became the 20th century. We had the 10 major questions in mathematics. And it happened again when the 20th century became the 21st century. A group of people got together and decided what are the 10 most important questions. Some had 20 that we needed to solve in the coming century. One of them is, what is dark matter? Seems a fair question. There seems to be a halo of invisible material in all galaxies, which we call dark matter. It's called dark because we can't see it. And that is observed or inferred from observations of gravity. You look at the galaxies, they seem to rotate in ways that are not expected based on the material you can see inside the galaxy. So that's why we think there's something more there which has gravitational mass but is not visible. We need to find out what that is. Dark energy. This was discovered more recently. We imagined the universe was expanding. Einstein accepted that when he removed the cosmological constant from his general relativity, the theory of general relativity. But more recently we came to see that not only is it expanding, but the stars farthest away from us are actually accelerating in the rate at which they expand away from us. Something is generating space-time at the far reaches of the universe, so that matter and space come into existence and force the expansion of the universe to increase in its velocity. This was observed by studying supernovae, which we think we understand. And the Nobel Prize was given to these observers in 2011. What is the lifetime of the proton, and how do we understand it? The neutron is not stable. The neutron in isolation decays to a proton, and lepton neutrino, the electron neutrinos. But the proton never decays. So far as we can tell, it has never decayed in the lifetime of the universe. The decay lifetime for the proton is more than 10 to the 15 years. Why? You couldn't be here if the proton decayed. All your cells would fall apart. So this is a basic question. Why is the proton absolutely stable? It's completely unnatural. All bound states that we know in all branches of physics except one fall apart into their elements. The hydrogen atom can easily break down. The proton does not. It forms the ground state. And that's why we can be here. The good news is you put the neutron inside the nucleus and the binding energy stabilizes the neutron too. That's why we can have nuclei. Then we put the pion in, it starts to bind them. All these things have to happen. But fundamentally, the proton is stable. Why does it happen and why is it so? And what physics explains the enormous disparity between the gravitational scale and the mass scale of elementary particles? Just think about it. The Earth is enormous. I can put a paperclip on the desk and I can pick it up with all the Earth trying to hold it down. But just imagine what you do with magnets when you try and bring them together, how much force you feel from these simple magnets. The disparity in scale between the forces is enormous, and we can't understand why that is either. So combining gravity with the other forces has long been a challenge, and we don't know how to do it today. And another one of the top 10 is, can we quantitatively understand quark and gluon confinement in quantum chromodynamics and the existence of a mass gap? This is tied up to proton stability, but it's a different question. You take a theory like QCD. I can turn off the Higgs boson, and the theory that is left over has no mass scale. It's a scale invariant theory. Scale invariant theories can't have any dynamics. They can't form bound states. And yet we are here. Something about QCD makes it possible for a theory without scale to acquire a scale and then generate the bound states that are you and I. This is the basic question of quark confinement. and the mass gap. How does a massless theory generate things with mass? The question of the existence of glue balls is tied up with this one, exotic hadrons, and ordinary hadrons too. So let's talk a little bit about quantum chromodynamics and what we know about it. It's the most important part of the Standard Model, and the one we understand least. It has matter, the quarks, and it has gauge bosons, the gluons. We think we know these things. We've had photons for a long time. They're gauge fields. We've had electrons. They're matter fields. This distinction between matter and gauge fields or force fields has been around since Maxwell. The Maxwell equations had force fields in them, and they connected electrons through forces. So it was distinguished between matter and force fields for 100 more years. We've known about QCD for 50 years. We discovered the quarks at SLAC in the late 60s. And only now we're just beginning to understand how QCD puts together things like the pion, the proton, and the neutron. Knowing how it creates even the simplest nucleus, the deuteron, is still far away. Making calculations based on QCD, directly tieable, connectable to QCD of the deuteron is yet impossible. So what is special about QCD? Well, the first thing is it's a theory, not an effective theory. This is a conjecture, but it's quite probably true, as we'll come to see. QCD is quite probably a self-contained and non-perturbatively renormalizable quantum field theory. That would mean it's well-defined. And that would be the first time we've ever developed a well-defined, internally consistent quantum field theory. QED is not such a theory. Electroweak theory is not such a theory. These are truly effective theories. They break down at a certain scale. I can take QCD in isolation, and it is well-defined. So mathematically well-defined. There is no confirmed breakdown over an enormous energy domain, 0 to 8 TeV. And it's increasingly probable that extensions of the Standard Model will be based on the paradigm established by QCD. Perhaps not in this elegant string theory or supersymmetry way. We might need to go the other direction and just accept that asymptotically free gauge theories have particular and peculiar properties that make them ideal for formulating as we go higher and higher in energy scales. An example is extended technicolor, where you have electroweak symmetry breaking via a new level of compositeness as you go down inside these particles. It was favorable. It went out of favor when string theory appeared. It's coming back into favor with the not observation of the particles that supersymmetry would predict. You can begin to formulate viable theories with compositeness of the Higgs boson and compositeness of other matter objects. In this type of theory, the Higgs sector becomes an effective description of some more fundamental theory based on fermions. People are looking at this. I'm not one of them, but it is viable. Our universe began with the Big Bang, the inflationary epoch, out here to the point of now, dark energy and the expansion. QCD's important part sits right down here, just after the end of inflation. 10 to the minus 6 microseconds after the origin of the universe is where the QCD phase transition took place. The Large Hadron Collider has experiments that focus on this part of the evolution of the universe. The RIC accelerator on Long Island, in the quark gluon plasma, for example. And all of the physics we're interested in these lectures will not lie there, but have its point in the evolution of the universe at that very beginning. So proton stability matters just here. Without proton stability, the rest of this wouldn't have happened. So we need to understand the proton stability from that point of view. This period, the growth of the universe would have stalled way back there, just in the microseconds after the Big Bang, unless the proton was stable. The deuteron formed, and so forth and so on. So the existence of our universe depends critically on a few facts. One of them I've already mentioned. This one, the proton is massive. The mass scale for the strong interactions is vastly different to that of electromagnetism. The proton's mass is 2,000 times that of the electron. The Higgs boson gives you electron mass. Something provides this magnification factor of 3 orders of magnitude that take you from electron-like masses, the Higgs boson couplings, to proton-like masses. As I said before, the proton is absolutely stable, despite being a composite object with 3 valence quark constituents. It doesn't fall apart. And yet the pion, which is made of the same types of things, is unnaturally light, but it's not massless. It is a composite object built from a valence quark and a valence antiquark. It has a lepton-like mass. It weighs the same as the muon, and yet it's made of the same things that produce a proton mass which is 2,000 times the electron mass. Something in QCD is making that happen. These are examples of emergence. We have very low-level rules producing high-level phenomena, and those phenomena are enormously complex. You couldn't be here without this set of simple facts. This pion is peculiar. It's essential for the binding of protons and neutrons into a nucleus, and it's essential that it be light. It was discovered in it was predicted in 1935. It wasn't discovered straight away. And when the first observation that they thought was the pion was actually the muon, because its mass is similar. It had to exist, otherwise you couldn't form nuclei. It has to be unnaturally light, because otherwise the forces would not act over a great enough distance to hold the neutron and proton together inside the nucleus. So without this, we couldn't be here. Quantum chromodynamics is therefore extraordinary. This is the first place that humans have discovered the collision between quantum mechanics and special relativity. When you try to match QCD with nature, there are all sorts of complexities you have to study. For a start, you lose particle number conservation. When you start to put particles, quantum mechanics, and special relativity together, you start to lose particle number conservation. I'm going to explain that. You find that things come to depend on frame and scale, and so the interpretation depends on the observer and the evolving character of the relevant degrees of freedom. In high-energy physics, the degrees of freedom are a parton-like quark or a gluon, a Higgs boson. But at our scales, the natural degrees of freedom are what? You can't break up the proton. You can't find what's inside it. You have to know what the degrees of freedom are you're dealing with. These things don't happen in electroweak theory because they're essentially perturbative. They don't have this sort of complexity. So how did this happen? What is going on in QCD? It's very simple, in a way. This is something which Wilczek included in a popular article he wrote, Physics Today. There is just one line here, and there are 2 definitions, the gauge field strength tensor and the interaction part for the fermions with the gauge bosons. And this is responsible for all of visible matter. So somehow, those few equations are able to describe how we came into a being. So it's quite possibly the most remarkable theory we've ever invented. That's worth solving. But how does it do all this? As I said, the Lagrangian is very simple. The most important piece is this part here. That's the gluon self-interaction piece. QED looks just the same, except for this term. And it's those self-interactions that somehow must be responsible for everything. You put an a squared term into the Lagrangian, and it generates all of the physics that describes the emergence of visible matter. You and I are made up of up and down quarks. The other quarks play a role in all sorts of physics. The strange quark is playing a role in low energy experiments, the charm you can measure, and so forth. But understanding us determines understanding how the quarks, the light ones, interact with the gauge bosons. And having the light quarks in the theory make things very different. You can compare this with quantum electrodynamics. As I said at the beginning, QED is the archetype for gauge field theory. It is simple in perturbation theory, but you can't define it non-perturbatively. It breaks down. The ultraviolet behavior, the high energy behavior of QED is undefined. The theory breaks apart. And QED predicts that very weakly, two photons will scatter from one another. This is a characteristic feature of the gauge theory, light by light scattering. Because the coupling is small, the probability of this event is of order 10 to the minus 9. So very difficult to detect. But it was discovered last year, a year and a half ago. At the LHC, the Alice experiment actually saw this effect. This is the popular image or discovery of the light by light scattering. So we can now verify that this event with extremely small possibility does happen in QED. So we've validated the theory at very, very tight level. It's a quantum field theory with this type of effect taking place. QCD has a similar type of interaction. Quarks scatter from quarks by exchanging a gauge boson. But it also has these gluon self-interactions, a 3-gluon vertex and a 4-gluon vertex. They're the special feature, the gluon self-interaction, that changed the character of the theory. This means that at tree level, there are gauge boson self-interactions. So instead of being a cross-section of the order 10 to the minus 9, it happens at leading order. It's a tree-level scattering effect. It's much stronger. And part of that effect was why Gross, Politzer, and Mulchek got the Nobel Prize in 2004 for demonstrating the role in perturbation theory of these types of diagrams. And the point of it is that in quantum field theory, nothing is constant. Everything is running. We have a distribution of charge and mass, and the number of particles, all things that quantum mechanics holds fixed, depends on the wavelength of the probe that you measure them. So if I have a long wavelength probe, I will see just one electron. But as the electron energy gets larger, or the photon energy gets larger, I start to resolve these virtual particle effects. What looked like just 3 objects now becomes 7, 8 objects. I go to higher energy, I get more and more objects. Particle number is not being conserved in the interaction. Couplings and masses are renormalized via processes involving these virtual particles. And such effects will make these quantities depend on the energy scale at which you observe them. So this is how the coupling runs in QED. As I go from 1 GeV to 200 GeV, the coupling changes by just 0.7%. We have a minus sign here because the fermions are screening the interaction. So as I get to higher energy, I see the coupling increase because I get inside that screening effect. If I add a 3-gluon interaction to this, then I have a completely different outcome. The coupling runs the other way. I go from 100 and come in, and the coupling changes by 500%. The fermion screening is still there. This minus sign is the same as that minus sign, but have an anti-screening effect. This plus 33 from the gluons. That is enough to change the coupling enormously. 5 times 10 to the minus 5 is the change in the QED coupling. I have a change of a factor of 5 as I go over the same length scales in QCD. And the coupling runs the other way. This effect is what they found. That running of the coupling with momentum translates into a running of the coupling with distance. Deep inside any hadron, the coupling is small. But as I try and take any two quarks within the hadron away from one another, this coupling grows. They start to feel a stronger interaction between themselves. And so that even at 1/8 of the proton's diameter, the coupling is now 1/2. It's very large. So this is partly where the origin of mass comes from. The vast majority of mass comes from the energy needed to hold the quarks together inside the nuclei. And that's part of the reason we have a confinement challenge. This is a very peculiar circumstance. The interaction that is becoming stronger as I take the object away from one another. If you think about magnets again, two magnets far away, you don't care. You try and bring the magnets together, the force gets stronger. In QED, it's the other way. Sorry, it's QCD, it's the other way. When the magnets are close together, they don't interact. But as I try and take them further apart, the force gets stronger and stronger. So it's a reverse or inverse magnetism. So way back when people first saw this happening, they thought that if the coupling grows so quickly, so strongly, perhaps it becomes unbounded. Perhaps it would require an infinite amount of energy to extract a quark or gluon from the interior of a hadron. This was the old notion of infrared slavery. But it leads to the confinement hypothesis, that color-charged particles cannot be isolated and therefore cannot be directly observed. They must clump together in color-neutral bound states. So we haven't proven this mathematically. We haven't proven it in any way. But empirically, it seems to be true. We have never seen a quark in isolation or a gluon in isolation. They always appear in color singlet final states. We have very energetic collisions at the LHC, for example. They produce lots of quarks and gluons at small length scales, but those objects fragment. They dress themselves up and reach the detectors as color singlet objects finally. So one of the basic questions inside QCD is, how do you understand this effect? You produce a quark and an antiquark deep inside a hadron with high energy. They escape from one another, and yet all you see that comes out are color singlet objects. That whole process is called fragmentation or hadronization. This is perhaps the most fundamental expression of confinement inside the standard model, because it involves these light quark degrees of freedom, taking this collision to color singlet final states. But this is all perhaps conjecture, discussion. The thing we know unambiguously about QCD is that we don't know enough. This is about all we know about the running coupling for certain inside the proton. So the nature of the interaction over 98% of the proton's volume is essentially unknown. We are making progress, and we'll talk about some of that progress this week, of how you know what the interaction is throughout the rest of the volume. But in perturbation theory, all we can prove mathematically is what the interaction is doing in this small part of the volume of the proton. The theory is asymptotically free. That means that perturbation theory is valid and works at large Q squared. What's particularly important in asymptotically free theories is that a chiral limit is well defined. That means you can define the question of what is a massless particle. QED can't do that. You can't have massless electrons. The QED theory doesn't work. Only with an asymptotically free gauge theory can you define a massless object mathematically. So it's important for all the understanding of pion physics, for example, the theory of QCD is asymptotically free. Yes? It's because as I try to take the chiral limit, I have to get to large scales to take away all the dressing. And when I push QED to the limit, the coupling blows up. So I have an enormous cloud to deal with. So QED is incomplete in the ultraviolet. So I can't get to the domain where I could define unambiguously what the chiral limit would be. The other way of saying it is that massless fermions in such a theory would propagate for very large distances. and something would have to stop that from happening in a quark-like theory. All sorts of feedback mechanisms start to take place that force you into this area. So QCD then is nature's only example of a truly non-perturbative fundamental theory, and the first one we've ever seen. So a priori, we don't know what this is capable of doing. Confinement. There is $1 million prize if you can solve the question of confinement. This was awarded, or would be awarded, by the Clay Mathematics Foundation. It was a prize. There were 7 such questions issued at the turn of the century, the year 2000. And part of the problem is to prove confinement. This is the part that makes the question peculiar. They want you to prove confinement in a pure Yang-Mills theory. Yang-Mills existence and mass gap. It says that prove QCD in the absence of fermions, mathematically complete theory, and has a mass scale somehow. If you can do that at a level of rigor that would be accepted by the people who asked the question, then you will be awarded $1 million. This group of people write textbooks about field theories in less than 4 dimensions. They have a very peculiar notion of what a mathematically well-defined theory is. So you have to have a very peculiar argument to answer this question. But also, there's another issue, is that the question is perhaps not meaningful. So we have to look at that. This is what hadron physics is about. Any class of subatomic particles that are composed of quarks or gluons we call hadrons. Proton, neutron, and pion are those objects. The word comes from hadros, meaning thick in Greek, and you put on the end because we do that with everything. A hadron, electron, proton, neutron. The baryon is a hadron with half an integer spin. Mesons are hadrons with integer spins. This is where we look at the proton and within. And when people start to plan for the future of hadron physics, for nuclear physics, to start building new accelerators and so forth, we have to have a reason for doing it. And people have argued that hadron physics is unique at the cutting edge of modern science because nature has provided us with just one instance of a fundamental strong interacting theory. And the community of science has never before confronted such a challenge as solving this theory. That was taken from the 2007 long-range plan for nuclear science in the USA. This long-range plan gave us the upgrade of JLab, the Jefferson facility in Virginia. It also set the stage for the beginning of the construction for an EIC, which we might end up doing, electron-ion collider, a new generation facility in the USA. Internationally, the hadron physics effort is worth about $1 billion a year in experiment and theory. Roughly 1/3 of that is spent in the USA. In the USA, about 90% of those funds are spent on experiment. Theorists don't cost much, and they're not worth much, according to some people. This is roughly the same budget that CERN uses to operate in a year. So it's the same level of effort as the operating budget for CERN. So hadron physics is a big deal. Internationally, a lot of people are investing their energy and their money in trying to understand what QCD is capable of doing. And we have a number of facilities that are trying to expose these things for us. In China, we have the Beijing Electron-Positron Collider. In Germany, we have COSY, ELSA, MAMI, and the FAIR project, which might start new generation experiments in 2025. In Japan, we have JPARC, which is complete and beginning new generation experiments now. We have the KEK facility, the Bell experiment. At CERN, we have the LHC, the ALICE detector, the COMPASS detector. They're both focused on understanding deconfinement and chirosymmetry restoration There was also LHCb. Now, LHCb was not meant to be a hadron physics facility, but LHCb is producing new hadrons, pentaquarks, peculiar objects that might well exist, systems with 5 valence quark degrees of freedom. We can't predict them, we can't solve for them, but it seems that they exist. And LHCb has seemingly discovered them. In the USA, we have JLab, this classic oval facility in Virginia. That cost $310 million to build. Well, actually, no, to upgrade. We just finished the upgrade of JLab. And on Brookhaven, on Long Island, we have the RIC facility, which uses heavy ion collisions to try and discover the nature of the phase transition that happened just a few microseconds after the Big Bang. And in the USA, with international involvement, we are looking to build now a new type of facility, the so-called electron-ion collider. There was one before, that was Hera in Hamburg. From the lessons we learned from Hera, we want to build something better. We want to build something which is very intense, very high luminosity. We don't need to go to the energy domain anymore because there doesn't seem to be anything at the energy frontier. We want to go to the precision frontier and start to look with high intensity beams to try and look for physics inside the standard model and physics beyond the standard model. So as part of the process for developing such a facility, the Department of Energy convened a special panel for the National Academy of Sciences to review the science case for such a facility. That committee released its report last year, and they found a compelling scientific case for the machine. They say that the EIC will answer questions that are central to completing our understanding of atoms, as well as being integral to the agenda of nuclear physics today. In addition, the development of an EIC would advance accelerator science and technology and would benefit all fields of physics through this type of technology spin-off. There are 3 main questions this facility will address. One is what I've been emphasizing. How does the mass of the nucleon arise? How does the spin of the nucleon arise? And how are the emergent properties of these dense systems generated by gluons? So this is very basic. The EIC will study the 2 fundamental traits of relativistic quantum mechanics. Back to the days of Dirac, it was recognized that there are just 2 observables that every observer can agree on: the mass of an object and the total spin of an object. M squared and J squared are Poincare invariants of the generalized Lorentz group. And the LHC wants to find out just what those things are and how they're formed. These are the only unambiguous labels that can be attached to any hadron state: the total mass and the total spin. Every observer will agree on that. And the EIC is dedicated to exposing the mechanisms in quantum field theory that create these fundamental Poincare invariants from the fundamental disorder in the theory. You make one gluon, it will never stay alone. It will make other gluons, quark-antiquark pairs. It will make a mess. And somehow all of this is what the proton is. And the idea of the EIC is to try and chart that effect and map out the distribution of all of these objects within the proton. And this is the densest type of condensed matter physics. There is nothing more dense than the interior of a hadron. This is hundreds of times more dense than the densest thing we can make. To approach these problems, we need theoretical tools. What should they be? Well, it's more than 100 years ago that Einstein took the first step for us when he explained the photoelectric effect through making this shift, changing the idea that light was a wave into giving light a particle-like character. Now, today, this might not look like much, but back then it was a really big deal. He was very modest According to the assumption to be contemplated here, when the light ray is spreading from a point, the energy is not distributed continuously over ever-increasing spaces, but consists of a finite number of energy quanta that are localized in points in space that move without dividing and can be absorbed or generated only as a whole. He didn't call them photons. That name didn't come until 20 years later, when chemists and opticians were looking at these things. But that was the big step, and he was awarded the Nobel Prize 16 years later for this explanation of the photoelectric effect. He and others, whose names you all know, spent their lives completing this picture of quantum mechanics for us. Einstein then also gave us, in the same year that he explained the photoelectric effect, the idea of special relativity. This is from the original paper. The laws of physics are invariant, that is, identical in all inertial systems, non-accelerating frames of reference. And the speed of light in a vacuum is the same for all observers, regardless of the motion of the light source. He said this in 1905. There was no one else at the time who was thinking about this. It was remarkable that anyone should think about this. And you all know what the consequences are, how it changes the way you look at kinematics and motion. This paper on the electrodynamics of moving bodies resolved the inconsistency between Newtonian mechanics and Maxwell's equations of electromagnetism, because they are Lorentz invariant. Maxwell's equations worked that way in the first place because they dealt with light. And also explained why you didn't see the ether, this supposed medium that exists in the universe to which the Earth is moving. This is the correct way to handle situations where the speed of the object is a measurable fraction of the speed of light. And special relativity is the most accurate classical model of motion at any speed where gravity is negligible. But that brought us to another era of Dirac. Once you have relativity, you have to change quantum mechanics, because the quantum mechanics of Schrödinger and Heisenberg was non-relativistic. Dirac gave us what came to be known as the Dirac equation in 1928. It's the first and only relativistic generalization of the Schrödinger equation for particles with spin half. But that equation also gives us the notion of antiparticles. And in Dirac's paper, he wrote the following: if we accept the view of complete symmetry between positive and negative energy electric charge, so far as concerns the fundamental laws of nature, and this is a basic feature of quantum field theories, although he didn't know that at the time, we must regard it rather as an accident that the Earth, and presumably the whole solar system, contains a preponderance of negative electrons and positive protons. It is quite possible that for some of the stars it is the other way about, these stars being built up mainly of positrons and negative protons. In fact, there may be half the stars of each kind. The two kinds of stars would both show exactly the same spectra, and there will be no way of distinguishing between them by present astronomical methods. And that's a problem, because antimatter is dangerous. Masslessness, the absence of mass, is impossible in non-relativistic theories. You must have a mass if it's a non-relativistic particle. Relativistically, masslessness is possible because Einstein's photon is a massless particle. Antimatter is negative energy matter. So for any given system, it costs zero energy to create a matter and antimatter pair, or 10 of them, or 100 of them, or infinitely many of them. Now, quantum mechanics as we know it is well defined. It can be used to treat a few bodies. Hydrogen is a two-body problem. The deuteron is a two-body problem. We can now, with the most sophisticated computers available and the best algorithms, solve directly for a 14-body problem. But we can't solve a 100-body problem or the infinitely many-body problem. So quantum mechanics is unsolvable when you have antimatter around, because you cannot control the number of particles that are going to appear. Relativistic quantum mechanics allows the existence of massless particles and antimatter. But both of those things destroy the stability of relativistic quantum mechanics. So the object that allows them to happen is the seed of its own doom. Relativistic quantum mechanics cannot be used to describe QCD. There's only one way to do it, and that's to invent relativistic quantum field theory. If you like to read books, you can read Weinberg's books on quantum field theory, and these statements are made there explicitly. Feynman, Schwinger, Tominaga, Glashow, Salam, Weinberg, Politzer, Gross and Wilczek, many other people have taught us how to deal with quantum field theories, at least perturbatively. And these form the paradigm for how we've developed the standard model. So a theoretical understanding of hadron physics requires the full machinery of relativistic quantum field theory. We have to reconcile special relativity and quantum mechanics. A long time, and questions still remain as to the way you might do this practically. The Poincare group has 10 generators. We have 6 associated with Lorentz transformations, rotations and boosts, and there are 4 more associated with translations. Those 10 together form the basis of special relativity's group, and you put them together to make quantum field theory. This generates or gives the idea of what the Hamiltonian should be. You have the questions of whether these generators commute or do not commute with the Hamiltonian, and that's where the interactions lie. So relativistic quantum mechanics predicts the existence of antiparticles. That is, equations of relativistic quantum mechanics give negative energy solutions. System is itself, particle, antiparticle, and so forth. And that's why we end up with this infinitely many-body problem. You can't do this in quantum mechanics because the problem there is that if the theory is formulated with an interacting Hamiltonian, if I put interactions into the Hamiltonian and I boost the bound state, then that boost operator will not typically commute with the Hamiltonian. So the wave function changes. And this takes us right back to the beginning when I said particle number was not conserved. If you have a relativistic theory and I give it any bound state a knock, then because the impetus does not commute with the Hamiltonian, the number of particles in that bound state will change. And so I have a new bound state. So I can't do overlaps anymore. Quantum mechanics is all about taking the initial state and the final state and making an overlap between the incoming and outcoming wave function in that simple way. If the wave function changes with the impulse, I must solve the new wave function problem every time, for every boost, for every impact. That makes a new calculation necessary in every frame. You can see this discussed in a number of books. This one I quite like, or articles by Brad Keister and Wayne Polizu, studying relativistic Hamiltonian dynamics in nuclear and particle physics, where these questions are discussed and approaches to them inside quantum mechanics are described. But the answer that we know of is relativistic quantum field theory. The example of a scalar field, you make a plane wave decomposition of the field, where these are now momentum-dependent creation and annihilation operators. And this is an uncountable infinity of particles, because these things are continuous. In that case, the non-conservation of particle number is not a problem. This is where virtual particles come into existence, in the decomposition of the field. But that opens up a whole area of other problems. In relativistic quantum field theory, you have loops generated by these virtual particles. And you have to solve those problems with the loops. And that's why Schwinger, Feynman, and Tominaga were awarded the Nobel Prize for being the first people to try and work out how you could cope with the divergences that these loop diagrams produce. When would you like to take the break, Johnny? Now might be a good time. And in Australia, we are sometimes too British, and we don't say very much to one another. And that means that lectures in Australia are very dull. The speaker speaks, The audience sleeps, and then everyone goes home. Maybe we can do something different here. So all relativistic quantum field theories can be treated in perturbation theory. Perturbative renormalization is a well-defined procedure, and we know how to do that in QED, we know how to do it in QCD and electroweak theory. But non-perturbatively, we don't. A rigorous definition of a theory requires that we do that. So to prove that QCD exists, we have to derive the renormalization constants, perturbative domain, but also compute them non-perturbatively, find out how they change, evolve. This is a way of defining the theory, because the renormalization group in quantum field theory is defined perturbatively. You can study how couplings and masses run using the renormalization group. But since it's based in perturbation theory, it breaks down when perturbation theory breaks down. So we can't use it today to prove that QCD is properly well defined. Hadron physics involves QCD. It is perturbatively well defined, but since we don't know rigorously how its renormalization constants evolve into the infrared, we cannot say yet that it is the theory of the strong interaction, because we can't prove that it exists. But that doesn't stop us. We're not mathematicians, we're physicists. We are quite prepared to make a guess and say, well, let's try it. What can we do when we have it? And that's how we make progress. We assume that somehow QCD is well defined and try and work out what the predictions are. And if we can make enough predictions and validate them empirically, then we can start to develop more confidence in the nature of the theory. Experiment's task is to explore and map the hadron physics landscape, such as with electron probes at Jefferson Lab. And why electron probes? Because electron is well understood. So the thing you're shooting is simple. And so what you see is probably a property of the target. So we use simple probes by preference. Theory, we employ established mathematical tools, and we refine and invent others in order to use the Lagrangian of QCD to make predictions. The hadron physics program worldwide in experiment and theory is to determine whether there are any contradictions with what we can truly prove in QCD. So far there aren't any, but there are still many, many puzzles and some controversies. But the great thing is, and why we keep building facilities, is that the interplay between experiment and theory is so fruitful. The feedback drives progress. We've learned a lot in the last 10 years, and in these lectures I'll cover just a few of those advances. Because a lot of the important questions inside the standard model, inside physics itself, lie in hadron physics. So we have to learn a bit about quantum mechanics first. I wrote Dirac's equation down very simply, the form that Dirac himself used. But it's more convenient to work with another form, which is explicitly Poincare covariant. And this is the object here, I d slash minus m. This d slash is just a combination of Dirac's matrices with the differential operator. And you can see this is Poincare covariant if you look at any one of the early textbooks on relativistic quantum mechanics. It's straightforward with simple algebra to demonstrate this. The object, which is the solution, is the fermion spinor, a 4-component column vector. This is the Dirac equation in the absence of interactions. This is the Higgs-generated current quark mass. If I put interactions in, I get the electromagnetic field, for example. It's just minimal substitution again, just like we always do in quantum mechanics. Use minimal substitution to put the photon field in there. And that gives us the interacting equation for a fermion with a photon. The typical procedure now is to find the solutions. So you consider the free field. And you suppose, as we've always done, that free fields propagate without interference, so a plane wave must be the type of solution to expect. Insert a plane wave solution. some column vector and a plane wave. This bracket notation is just k contracted with x in whatever metric you like to use. If I do this, I have two types of solutions, one with a minus sign, one with a plus sign. I put them in and I get two separate types of Dirac equation for the free particle. They're qualitatively different types of solution, plus k and minus k. And this is the antiparticles that Dirac taught us about. Plus k means positive energy, negative k means negative energy. So you see very straightforwardly that just the first simplest analysis of the Dirac equation leads you to antiparticles. If we assume the particle's mass is non-zero, then I can work in the rest frame. And then k slash is just gamma naught times k naught. That's what I've written down here. The particle's at rest, I've factored out the mass, and have two very simple equations now for the spinor object u, or v. And there are clearly two types of solution. One of them has entries in the upper two components, and the other in the lower two components. These are the particle-like solutions, these are the antiparticle-like solutions. You see there's one more degree of freedom, and that's the spin. Dirac's equation was peculiar and a big advance because it predicts spin. The Schrödinger equation, you have to put spin in by hand. There is no classical analog of the spin of a particle. It's not things spinning like this. It's got nothing to do with that. We call it spin because it's simple, but it has no classical analog. It's a new quantum number. That's what it is. Up or down, you could call it anything you like, but it's not anything about spinning. I have now to go from the rest frame into an arbitrary frame at a given momentum. You can do that by applying a boost. It's a non-interacting theory. I have a boost operator. I can boost the solution. But there's a simpler way of doing this. You just look at this identity. I have k slash minus m and k slash plus m. Together they make k squared minus m squared, and that is 0 for a particle on shell. This is just Einstein's condition, equals mc squared at arbitrary momentum. That way, I now know that this combination is a solution of this equation, because k slash minus m on k slash plus m equals 0. So I know what the answer is now in an arbitrary frame. This u is just the vectors I had before. So this then is the complete solution for a free fermion on shell in an arbitrary frame of reference. Just a couple of simple lines. I can do the same thing for the antiparticle. I now have the minus k slash plus m, and you see something's changed. Here I have e plus m over 2m and m squared down here. This flips when I get to the antiparticle. You see the sigma dot k in the lower components. This says that when the momentum of the object is small, I can forget the lower components. This is how I get Schrödinger's equation back again. When the momentum of the particle is small compared to its mass, then I have Schrödinger-like mechanics, quantum mechanics. But the antiparticle is completely different. It's irrelevant at low energies, like small momenta, but comes to play an important role at high momenta. This works because there are only two linearly independent solutions for the free field theory. That's why it's so simple to solve this. When you're dealing with quantum field theory, there are some analogies to quantum mechanics. I'm going to need to define an inner product. I'm going to need to take an overlap of a fermion with an antifermion of sorts. So I have to define what the conjugate spinor is. So I take the normal spinor, I take its Hermitian conjugate, I multiply on the right by gamma naught, and that gives me psi bar. And that is the object needed to make the inner product in a quantum field theory. This then gives me conjugate spinors. And it's not surprising that they are just the U bar object with the same type of matrix structure on their right. And as always, I have orthonormalization conditions. These spinors must be orthogonal and normalized. I'm doing a quantum mechanics after all, in some simple sense. From this point, I want to find a way, taking any fermion, to project out the positive energy part and the negative energy part. I'm going to need to use this to find out which states are going to make it to my detectors, for example. Typically, there'll be positive energy particles making it to the detector. The negative energy ones get eaten. I look at my spinors. I have a sum over 1 and 2. I take the spinor and the conjugate spinor, U bar. Because I've put them back to back in the reverse order, the answer is going to be a 4x4 matrix. I now look at the orthonormality relations, and I can validate these statements, that lambda plus on the positive energy spinor gives me the positive energy spinor back again. But if I put lambda plus on the negative energy spinor, I get 0. So this simple construction guarantees me a positive energy projection operator. In the rest frame, I know what these spinors are. They're very simple. I just get this matrix. And that's 1 plus gamma naught. In an arbitrary frame, I use the same trick as I used before, and I can argue myself to the point that this is the general form of the positive energy projection operator, just k slash plus m over 2m. You can all do this very simply. You don't need more lines than I'm showing here. The negative energy projection operator is very much the same. I take the negative energy spinors, I put them back to back again, and I find it's minus k slash plus m over 2m. And these are typical projection operators. I square the operator, I get the operator back again. I take the trace, and I get the sum of 2 entries, both of which are 1. And that's true in any frame, because of the special properties of the Dirac matrices. And if I add them up, I get the identity matrix back again. So it says that the space of fermions breaks up into 2 sectors, one of them having positive energy and one having negative energy. And only interactions will connect them. I cannot turn a particle into an antiparticle unless I put interactions in. So these things propagate forever unless I do something to them. And those spaces of the quantum field theory are independent unless I put interactions in. When you start to deal with quantum field theory, you start to ask the question, how do I solve these equations with interactions? So the Dirac equation is a partial differential equation. Now, those of us who have studied the mathematics of partial differential equations know that the simplest way to solve them is to work out what the inverse of the differential operator is. We call it the green function. You take the differential operator and you work out what type of thing there is that is the inverse of that operator. So let's look at the Dirac equation with an electromagnetic field in there. The solution of this will give me the fermion behaving under the influence of this electromagnetic field. How do I define the inverse? Well, this is the mathematical definition. I take the operator, and the inverse is that object for which this product is equal to the 1 in the matrix space and the delta function in the functional space. Now, if I use this quantity, this object here must give me the wave function at a new point. That's obvious because if I now act with this on there, because that's the delta function, I get the thing at the new space-time point. That gives you the strength of this propagator. It's the general solution of the Dirac equation given any initial condition. And this is something you all know because this is Huygens principle. It just says I have a wavefront. And choose the wavefront, take any point on that wave function, on that wavefront I should say, And the wave at another point is just the sum of all the contributions from the original wavefront. And that's what this is doing. I take the original wavefront and with the propagator sum over all the points on the wavefront and take them to the new direction, or new position. So I'm using Huygens' principle to solve the Dirac equation for the field at an arbitrary space-time point given the initial conditions. And this is useful, of course, because in any physical theory, the interaction I use will be bounded, will be compact. The interaction won't extend over all space-time. There'll be some source, it'll be localized, so I can start with a plane wave at infinity and bring it in slowly, and it will scatter. And so I can use, in extreme conditions, a plane wave here, and then once I know the propagator, can communicate that plane wave to the interacting solution at any point in space-time. So that's why propagators are so crucial, because they are actually the answers to the question of what is the fermion wave function anywhere. As I said, this approach is practical because all physically reasonable systems can only be non-zero in some compact subdomain of space-time. So the solution of the complete equation is transformed into solving the green function only. The point that makes it difficult is that this is actually impossible in all but the simplest cases. There are some very simple cases where you can compute this propagator exactly. An example is a constant background magnetic field. There you can solve it simply. An electric field is harder. Having a background field with space-time dependence is harder still. Having a general background field is impossible. But these books, I show you some cases where an exact solution is achievable. Let's try and do it more generally. This is the Dirac operator without interactions. I want to find the inverse of the Dirac operator. The typical way to solve any problem in physics is to make a guess. So you make a guess. There is going to be some plane wave-like behavior because this is a free particle, and some matrix. So let's assume a form like this and insert it into this equation. And then I find, yes, it works, so long as this matrix S0 satisfies this equation. And you know what the answer is to that because I showed you earlier. It's just p slash plus m over p squared minus m squared. This is almost well defined. We just have a problem at p squared equals m squared. And that condition, what happens at p squared equals m squared, is tied to a boundary condition. Remember, this is a differential equation. It's first order. To define the solution, I need to have one external condition, the boundary condition. So what will we do? Let's be sensible. This is an object that should take a positive energy fermion to a positive energy fermion somewhere else. So I want it to propagate positive energy fermions forward in time, but not backward, and negative energy fermions backward in time. If I do that, then I get the plus I eta prescription that is popular. It's called the Feynman prescription. So a wave function for a positive energy free fermion is given here. I take the antiparticle, that's this charge conjugation matrix, and a transpose. You can now show that with these identities, this object must contain only positive frequency components for times x0 minus x0 greater than 0. That means it must be proportional to the positive energy projection operator. But you know that, because that's what the positive energy projection operator is, p slash plus m. So at the end, you put this boundary condition in there. This then is the Feynman propagator for any fermion. This is valid for any quantum field theory. The fermion you use in perturbation theory is always described by this simple propagator. At the end of any calculation, you take eta to 0 from above, and you'll have a well-defined case where the singularities have returned to the real axis and only physical singularities remain. The interacting problem can be solved in this way, sort of in general. I want to solve the interacting Dirac problem. I want to solve its propagator. Getting a closed form is impossible in all but the simplest cases, as I said. But what people typically do is use perturbation theory. So you take this equation and you rewrite it, put in the interaction on the other side. If this is a small or weak interaction, it can be considered as just some minor perturbation. And now I make the full propagator as the sum of the free propagator plus the full propagator, the interaction, and the free propagator. And I can expand that order by order in the coupling. And you can show this yourselves in a few lines that this is the general solution to that problem. So you can solve this equation in perturbation theory. And this is actually a definition of perturbation theory. It says that the dressed propagator, the propagator in the presence of interactions, is the free one plus some number of scatterings from the source. And depending on how accurately you want to solve the problem, will be telling you how many terms in the perturbation you keep. So this is the perturbative expansion of the full propagator in terms of the free propagator. And that's how you build up perturbation theory. This is solved in many textbooks. One case is an electron or positron being scattered by a Coulomb field. An old book by these Frenchmen discusses that in detail. And this one is a very special equation, which actually the Dyson equation. Freeman Dyson never won a Nobel Prize, but he contributed a great deal to the development of quantum field theory and many-body theory. And one of the things was the Dyson equation, which is just this one here. The green function has the following interpretation. It creates a positive energy fermion at a space-time point x, or a positive energy antifermion, and it propagates that fermion to another space-time point, which is at a point later in time. And it then annihilates this fermion at the point x prime. This is, in a sense, Feynman's interpretation of the propagator. You can view this process a different way. You create a negative energy antifermion at x prime. You send it backward in time. Then you annihilate it at the original point. So if particles going forward in time, antiparticles going backward in time. The one propagator describes both. This is the merit of the fully Poincare-covariant treatment of quantum field theory. You don't have to worry about the time ordering of diagrams, because all time orderings are present. Yes? At this point, yes. But it's also what people are doing in quantum field theory when they solve loop diagrams, for example. So they're using the same types of ideas, but here I'm introducing them to you from the point of view of quantum mechanics. So you can see how relativistic quantum mechanics naturally leads you to the point where you start to see scatterings. Scatterings, you're going to find loops, and you get divergences, and there you get quantum field theory. And all propagators have the same type of interpretation. I can do this for photons, for gluons, for W bosons, and so forth. This point, I'm going to stop and ask, are there any questions about relativistic quantum mechanics you'd like me to clarify before we move on? We had a little, yes. Yes. Effectively. That's what it does, yes.
So this is the physical interpretation of this. It represents boundary.
It's what it does, yes.
So what's the physical interpretation of taking eta equal to 0 at the end?
So when you have this propagator, we'll see this shortly, but I'll do it quickly here and we'll do it again. That appears in the denominator. Clearly, this particle is on shell, which means that p squared equals m squared. So this is 0. So it's meaningless. I have to give some meaning. If I plot this in the p-squared plane, this propagator has a 0 here and here. And I'm integrating along this line. And I can't cope with that. So I have to shift the singularity off the axis, put it back down here and here. So now my singularity is away. I can do all my calculations. But since the solutions should not depend on the mathematical tools I use, in the end, I must find a solution that doesn't care about what eta was.
So we say we have a differential equation which requires a boundary condition if we want to have a solution.
Yep.
Now we're saying we don't want boundary condition if we want a solution.
I see what you're trying to say. What's important is the way you're doing this. That one goes that way and that one goes that way. That's where the boundary condition still remains. So when I take the limit again, this comes from there and this comes from there. That's how the boundary condition gets in. That's right. If I put it both of them down here, that's a different propagator. I can still define the problem, but I'll have an advanced or retarded propagator. So I have three choices. This is the Feynman prescription, and it's one we use for Poincare covariant treatments of the theory.
My question is, this is how we interpret the existence of this eta, or in other words, the choice of the so what's the eta going to zero?
Physical interpretation of eta, there is no physics in eta. There's a physics is lying in how I choose to distort my contour. So by doing this particular prescription, I'm saying I want my object to propagate positive energy fermions forward in time.
Okay, so in other words, you can forget about eta and just take principal value.
Up to a point, but you know principal values aren't easily defined with multiple loop integrals. So you need to have a prescription you can use everywhere. So if I get overlapping divergences and I try to say I'm going to take a principal value, I'm going to have a bit of trouble because I have nested integrals all the time. And this prescription allows me to deal with that in a very precise way.
So still have this problem that we introduce eta as something that represents some physics. At the end, we say it doesn't represent any physics, so let's get rid of it.
That's a misquote. The point is, the direction in which I distort the contour is the physics. The fact that I've shifted one up and one down is where the boundary condition is. That I've taken a positive energy fermion at infinity. Yep. After that, I get rid of eta, but I've kept the fact that the contour was distorted in a certain well-defined fashion. Yes?
How does the way you organize these tools relate to the initial condition?
You see this? It says exercise. You can do it. What you do is if I have these distorted this way and this way. Yeah, this is, yeah. What this says, I'll answer this one quickly nonetheless. Having one up here and one down here means that if I take the contour this way, or I take the contour this way, I'm going to get something from both up and down. This is the one that says positive to positive. I could have taken them both down here, and then I would find nothing up here. And that would say this positive one doesn't go anywhere if the time ordering is a certain way. So it stops it from happening. So by distorting the contours down or up or either way, it changes which object is propagated where. So I can get retarded propagators, advanced propagators, or the Feynman propagator. And if you follow this mathematics, you can show yourself how this happens. So, local gauge theories. QCD is one of them. That's the basic way we build the standard model. They're difficult to quantize because the gauge dependence is an extra degree of freedom. And it's not dynamical. Nothing in a field theory can depend on the way I choose to quantize it. And the choice of gauge is a choice in the quantization scheme. One approach, and one we often use, is the functional integral formulation. You can look at this textbook, or this one, actually quite useful. This comes from, again, Feynman, who'd had a path integral formulation of quantum mechanics. It's not so useful for quantum mechanics, but it's extremely useful for quantum field theory. You promote the fields to the integration measure, as we'll come to see. In general, mathematicians don't regard local gauge theory functional integrals as well defined. Mathematically, these things don't exist. We use them anyway. And you and I are here, so they can't be too bad. So it's long been known that you can derive from these field equations a certain collection of equations of motion. The first one, as I said, was by Dyson, the Dyson equation in 1949. Then Schwinger made the whole process systematic in terms of what's called Schwinger source theory. It's not a transparent formulation of the approach, but it does work. This collection of equations is called the Tower of Dyson-Schwinger equations. They're the field equations for quantum field theory. And it's intrinsically non-perturbative. And that's important for dealing with non-perturbative quantum field theories. At the other level, you can recover all of the diagrams in perturbation theory using this approach. And that's important because that's how you can prove renormalizability. So QED, the proof of renormalizability within the domain of perturbation theory, can be done using this collection of Dyson-Schwinger equations. And it can't be done any other way. You have to be able to connect a given endpoint function, a given 3-point vertex or 4-point vertex or interaction, to all of the other ones to prove that the renormalization constants you've used at one order are completely sufficient to describe and eliminate all of the divergence in every other diagram. And the only way to do that is if you have a way of relating a multi-point diagram to something with lower order. So at the basic level, these things are used to prove renormalizability. Let's try and derive one. This will be the hardest mathematics I talk about, so please pay attention. This is the action for QED. I have the fermion term, bare part, interacting part, the gauge field tensor for the photon squared, and the gauge fixing term. Now these fermions, when I describe this in quantum field theory, are called Grassmann elements. It simply means they anti-commute. So psi times psi is always 0. The only thing that's not 0 is psi bar contracted with psi or psi bar. This is just the way of embedding in quantum field theory the anti-commutation relations. These are the bare masses, the bare charges, and the photon field. And by convention, we say the electron has negative charge. I could have called it positive. It's just a matter of choice. And all the theory, all of the interactions in QED, are said to be given by this rather compact formula. It's in fact very complicated. It says that I must integrate over all possible configurations of the photon, all possible configurations of the fermion and the antifermion. I must weight them by this exponential and put these source terms in. Then I am supposed to achieve a description of everything that QED can describe. This was W, the generating functional for the action. When you formulate the theory, you typically introduce Z in this exponential, because this quantity generates connected green functions. If I stayed with W, this quantity here, this would also produce one electron and another electron propagating without talking to one another. I don't care about that. If I've already solved for the one electron problem, putting another one in doesn't hurt me, doesn't help me. So I don't want to deal with W. It's got too much information in it. I want something more compact, and that is Z. By exponentiating this, I take care of all the cases where I can have all these things just propagating side by side without talking to one another. Now I want to derive an equation of motion for this quantity Z. And it's very simple. You simply observe that if I integrate a total derivative and I choose the boundary conditions properly, then the answer is always 0. There's no information contained here. Derivative of f integrated is 0 so long as the function is either 0 at the boundaries or it's the same as itself at the boundaries. Well, as we've said many times, in all physical circumstances, there's no interaction at the boundaries, so you can think this is 0 at the boundaries. Then you can start to work with this. I have W, I have Z. If I differentiate this, I must get 0, because the fields are all 0 at the boundary. So I have an answer which is 0. I can differentiate this whole object, and I have a functional differential operator acting on W. This is one of the exercises with the tutors, so it's worth looking at it. Yeah.
You said that on the boundary it's 0, but what about electromagnetic field?
I would typically solve a problem with a finite electromagnetic field in some compact domain. So suppose I have the sun.
There is no problem with long range.
The field is still 0. The photon field propagates with a 1 over q squared type of damping. So my wave function for a field is still going to be 0 at the boundaries. Think of the sun. Right? The sun's light propagates to the end of the universe, but very, very slowly, in a sense. The universe is so big. So I can always choose a domain big enough where the boundary values of the field are 0. And if I can't, then I can't solve the problem. Because this is a peculiar sense in which the whole universe is filled up with some force that is having an impact on me. That might be the ether that we talked about, that Maxwell, Michelson and Morley had, for example, this force that travels through the whole of space-time. But in any thing that we can create here, the fields are always going to be 0 at some boundary. If I do that, then I have a functional differential operator acting on this W. This is like a normal differential operator, it just involves some contractions. This is 64, I put that into here, and I differentiate to find what the derivative of the action is with respect to the photon field. I get this simple term. It has something acting on the photon field and something involving a fermion current. So the equation for the field, or Z, now becomes this one. I have a source term, I have an operator acting on this derivative, and some differential operator that's representing this current. And I've taken a divided by W all the way through, because W is just some number in the end. And this, in fact, is a representation of Maxwell's equations. It's a compact way of writing down Maxwell's equations in the interacting case, but maybe it's not transparent. One more step. You introduce the one-particle irreducible green functions. Not just connected now, but one-particle irreducible. Because I don't want to have computed the whole problem and then convolute it with another one and another one. I want to get the germ, the kernel of this. Then I can build it into everything else. So in a sense, this is like taking the inverse of a propagator, because all the complications comes and expand in the inverse. So if I have the inverse directly, then I don't have to worry anymore. That's what gamma is. There's a Legendre transformation. Again, if you study simple functional methods in mathematics, all of the tricks still work, just generalized a little bit. So Z is equal to gamma plus these sources. Photon, source for the photon, fermion, source for the fermion, antifermion, and source. This object generates the endpoint or proper vertex functions. So I can't take this now and break it up by taking any one line out. It's intrinsically connected. It's an overlapping diagram. And you can look at many textbooks to get this clear. From the definition of the generating functional, these identities are obvious. Let's look at one of them. Here, I take W, I differentiate with respect to J, I'm going to get A back. All of these things happen in very simple ways. So dz dj gives me A, dz d psi bar gives me psi, and so forth. And for this present time, I'm keeping the external sources to be non-zero. At the end, I'll set the source to 0, and then all my fields will vanish. In gamma now, I can verify that the derivative of gamma with respect to A is just the source term. So I have this mirroring between the generating functional of connected green functions and the generating functional of one-particle irreducible green functions. Since the sources are not 0, then A is actually a function of the sources. This is how I tell nature what interactions I have. So if I'm an experimentalist and I want to make some magnetic field, I've actually created a source for the electromagnetic field. I've made a J and given it some structure. And the same things are true for these derivatives with respect to the Grassmann variables. I now consider a product of two derivatives. I differentiate Z twice with respect to the fermion source and the antifermion source. And I differentiate gamma with respect to the antifermion and the fermion. And at the end, I'm going to set everything to 0. If I look at this, and then go back one step, look at these correlations. It's evident that this is just this, differentiating the source with respect to the field. And this one, differentiating the field with respect to the source. Now, the usual rules of differentiation, this gets killed, and I get differentiating an object with respect to itself, I'm going to get the identity matrix. Identity in space, identity in matrix indices. So this contraction is 1. Now where does that come into your head? Remember how I defined a green function? It was the inverse of a differential operator. This I know to be a differential operator. It's Maxwell's equations. So I'm giving you a definition of an inverse here. I go back to 67, I look at what this is, and I find that this derivative, d gamma dA, is this object acting on there. Look at that. That's just the differential operator describing the photon field. And now there's an interaction term, which has this trace of what is the fermion propagator. So just looking here now, I have the inverse of the propagator. This is the general feature. The functional derivative of the generating functional for one-particle irreducible green functions is the inverse of the propagator. It happens everywhere. It's always the same. The in-vacuum fermion propagator, or in another word, the connected fermion two-point function, is this object with the external source set to 0. There's no external field. This is my propagator. And these are the green functions of quantum field theory. I started with the generating functional for QED. I did some simple mathematical exercises, and I arrived at an equation for the propagator. Here is the analog for the photon, the second derivative of gamma with respect to the photon sources, set all external sources to 0, and I get this object acting on the delta function, and this complicated term. It's a derivative of an inverse. That is going to be the photon's propagator, inverted. And I have a complicated right-hand side now. This derivative of the inverse of something which itself is an inverse. But you know how to deal with that. You go down to matrix theory. If I take A, multiply it by its inverse, I get the identity. The derivative of a constant is 0. And that says the derivative of an inverse is just negative, the object itself, the derivative of A, and the inverse. So I'm not doing anything new here. We knew this from matrix theory. So this expands to be this triple product. I have an inverse, which is a propagator, the fermion propagator. I have an inverse, which is the fermion propagator. And I have an interaction term. This vertex differentiated 3 times. If I deal with perturbation theory, I can compute that, and I obtain the free fermion gauge boson vertex. So this might look like a hard way of doing it, but I just start with the Lagrangian of QED, use some simple mathematical tricks, and arrive at this result. And that then, this interaction piece, is what we call the photon vacuum polarization. Every tricky thing that can happen in QED to the photon is contained here. This photon vacuum polarization describes the modification of the photon's propagator due to the presence of virtual particle-antiparticle pairs. The running coupling constant in QED is in here. Part of the Lamb shift, which is observable, is in there. How the rho meson decays into E plus E minus is also in there. So with just a few lines of algebra, you have arrived at something which is crucial. It's the photon self-energy. The inverse propagator can be written as the leading piece plus the polarization, which is the interaction term. The free gauge boson propagator is very simple. 1 over q squared, with the I eta again, because I want positive energy particles going to positive energy particles, plus a gauge fixing term, because I have this residual degree of freedom in the theory. This has a diagrammatic picture. The vacuum polarization, the photon comes in, it breaks up into a fermion-antifermion pair somehow, and then annihilates into a basic photon. Then this is the seed term for the Dyson equation for the photon propagator itself. This is the inverse propagator. It sits in here. And then I expand the inverse and I get 1 interaction, 2 interactions, and so forth. So I have now used a non-perturbative method to arrive at an equation whose expansion reproduces the perturbative theory for me. The residual degree of freedom is the gauge fixing term. You can use anything you like physically. No answer should depend on that. And so in perturbation theory, people will often calculate in a couple of different gauges and just validate that those terms that depend on the gauge don't contribute to anything physical. They cancel. You can prove this non-perturbatively just by using what's called the Ward-Green-Takahashi identities. This lambda naught, if I choose it to be 1, I get Feynman gauge. If I don't worry about this pi in the propagator, so I'm dealing with perturbation theory, then that term cancels this term, and I get a very simple propagator, just g mu nu over q squared. That's very easy to work with. But that's not very useful non-perturbatively. Because non-perturbatively I have this pi here. And you see those two terms don't cancel when interactions are important. So any non-perturbative treatment of the theory, it's best to use Landau gauge, where this term vanishes. So that's typically why people use Landau gauge in any practical computation non-perturbatively in any theory. The Ward identities are critical in quantum field theories. This takes us back to the good old days of physics. This is a PhysRev letters by J.C. Ward. It occupies less than 1 column in a page of the journal. And it's one of the most important identities in physics. It helps to prove that QED is renormalizable and that the photon vacuum polarization contains everything you need to know about the running coupling in QED. There are a whole array of Ward-Takahashi identities. Ward was the first. Green and Takahashi generalized these. This is the Green from Adelaide University. His name was forgotten for a long time, but we remembered him recently. These have physical implications that go everywhere. They have generalizations to non-abelian theories, as the Slavnov-Taylor identities. And what they're telling you is that this vacuum polarization has special properties. It can only appear in the transverse part of the photon propagator. It can't appear in the longitudinal part. That's just confirming that the gauge dependence in the theory is not dynamical. All dynamics is contained in pi. If pi mixed with the lambda part, then we'd have a mixing between the gauge dependence and the polarization. That would break the fact that gauge invariance is a symmetry. There is a photon vacuum polarization analog. This is the self-energy for the fermion. Fermion coming in, breaks up into an electron-photon pair, propagates, annihilates, and so forth. This is the green function for the interacting theory. And this is my dressed propagator for the fermion. It has the self-energy in the denominator, just like the photon had the vacuum polarization. Diagrammatically, this is the picture. Photon or fermion propagates, emits a photon, reabsorbs that photon. And this happens ad infinitum. And then I expand that or continue that to get the whole sum. And this is called the gap equation. And the reason it's called a gap equation goes back to Dirac. When Dirac was formulating his fermion theory, he realized there were negative energy particles. He had to fill up all the negative energy states to form a stable ground state. And there was a gap, which is twice mc squared. This is for free fermions. This gap changes under the influence of interactions. And so this is why the equation describing how the fermion propagator changes under interactions is called the gap equation. Because it gives you the answer on how the gap between the negative energy C and the positive energy states is changed under the influence of interactions. Let's just do one quick perturbative calculation. The gap equation, I've taken the flavor label away. This is QCD now. I've put a Gell-Mann matrix in. And now this is the gluon two-point function. This vertex, we'll look at the free vertex. And now I have a simple loop integration to do. One gluon, one quark, bare vertices. That is this integral. There are many ways of handling this. A simple way is to complete the denominator, bring a bit of the denominator to the numerator, act on the algebra, and from this simple expression, you can get to a statement about the self-energy. If we look at the last term, you find very quickly that it vanishes. Because no matter how I regularize the theory, so long as I do this in a Poincare covariant way, it cannot depend on the sign of the momentum. It integrates out. So that part's zero. There's another part. Let's look at the second term. I have this integral now. I have an ultraviolent integration to complete. This integrand behaves at large k squared in this way. But I have a measure factor here, which also has a k squared in it. Here comes our contour prescription. I have a singularity down here and one up here from my I epsilon. I can make a wick around this way. Now integrate here, no singularities. And this integral becomes this one. There's a four-dimensional measure factor. So the angular integral can now be done in a very simple way. And my answer is just infinity. It's meaningless. This is the whole problem with quantum field theory. And this is why Schwinger, Feynman, and Tominaga were given a Nobel Prize, because they could work out what to do with this. you have a divergence in the integration which you have to deal with by renormalization and renormalization. Such ultraviolet divergences appear everywhere. There are also some infrared divergences that happen in theories when I take the mass scales away. The problem in renormalizable quantum field theory is you have to prove that I can make the theory sensible with just a finite number of renormalization constants. QED there are 3, but because of the water density there's only 1. In QCD there are 7. Then I absorb all of these divergences into renormalizations of the couplings. And that regularization procedure must preserve the Ward-Takahashi identities, these conservation laws. A theory is called renormalizable if and only if the number of different types of divergent integral is finite. So in QED, there are superficially 3 different types of divergence. But because of the water density, there's only 1. And that 1 is related to how the photon coupling runs. In QCD, there are 7, and you must keep them all. This is the result in QCD for the self-energy of the fermion at 1 loop order. This is the vector part, this is the scalar part. Because a fermion has 2 different terms, a Dirac matrix term and one that's independent of the Dirac matrices. You can see if I choose Landau gauge, the vector part is 0. That's a general result in quantum field theory that the vector renormalization of a fermion propagator always vanishes at 1 loop order. That's another reason to use Landau gauge, because you simplify your fermion propagator. There's another one. The scalar part has the current quark mass there. This is the running coupling, that's the running gauge parameter, it's 0, and I have a running mass. The theory is asymptotically free. I've given you the 1 loop order expression, and I see the scalar part of the dress self-energy is proportional to the current quark mass. This piece here, at 1 loop order. If I do it 2 loop order, or 3 loop order, or at 100 loop order, I still have proportionality to the current quark mass at every order. So if the current quark mass vanishes, then the scalar part of the self-energy vanishes as well. And that tells you there's no chiral symmetry breaking in perturbation theory. No matter which order you approach the theory, if they start with a massless fermion, the fermion always remains massless at any order in perturbation theory. So that means if I stay with QCD, I use the massless theory, then we still can't be here. No order in perturbation theory can generate a mass scale in QCD. So these are the questions we have to solve. We have QCD. It's an interacting non-abelian gauge theory. I can put the mass equal to 0 because the current quark mass for the up and down quarks is very small. It's much smaller than the scale of you and I. And yet somehow we have to exist from there. So all the techniques we know about rigorously in mathematics are unable to solve that question. So our task is to address these issues in QCD. Basically, that $1 million question has to be solved in the real world where there are light quarks. That's enough for today. Thank you for your attention.